how human is behaving. So it is detected by the robotic arm. Then the laser projection, because when we are speaking on the particular component, so it is about laser projection. So that was the three different aspects which are demonstrated in the earlier video. So what is about robotic path planning and obstacle avoidance? So it's about the path planning. First is about for path, like from A to B. It has to plan the path from A to B. Then second is if there is some obstacle in between, it has to detect that obstacle and check if the obstacle is safe or not. If the obstacle is not safe, that has to find an alternative path to avoid that obstacle. So if the path is safe, then the robot has done this operation. So in this way, there is a path planning process and with obstacle avoidance. So there will be 2 points initially from path A to B where the robot has to go, and the second is to detect the obstacle in between. If the path is not safe, obstacle is there, then find the alternative path and reach the goal. So there are many methods of this path planning. So later on we'll discuss about today's method of traditionally like gradient method with Newton's method with Lagrangian minimization principles, or there are different other methods. First one is artificial potential field for path finding from from start position to goal position. It uses the relative repulsive and attractive potentials within the environment. What this does is actually the goal point is the attractive potential, where it attracts the field area, and all the obstacles will be your repulsive potential which repels each other. So with the attraction and the repulsive potential in the closed environment area, this algorithm works, where APF is proportional to the distance between the trajectory and target points. It also inversely proportional to the distance between trajectory point and the obstacle point. So there are, you can see the graph, the small arrows which are nearer to the goal position. It is the attractive potential, and which are going to repel these attractive position from the obstacle. It's the repulsive potential. So there are 2, attraction and repulsive, and the total potential field will be the addition of these 2, attraction and repulsive potential. So this is the method which can be used for finding the path, shortest path between the start and the goal. There is one more traditional method, it's called as the history algorithm. It is actually a grid-based method. So here in all the space, it provides a grid, and each node, each next grid is calculated from the first grid. So every grid is first calculated and find out the node, the goal grid, which is here, and then each grid is calculated and find the path to the goal grid. So this algorithm works with the grid-based approach or the node-based approach. And in this way, what the solution was, it uses first to calculate whole surface, whole area, whole space. So the next algorithm A star was introduced, which also gives the cost function of the node area. So here there is a heuristic cost function on the node, which is improved from the history algorithm, and here whole space or whole surface is not used for the calculation. So it is more, it's about point-to-point obstacle, and here there is also a grid-based node, but the node for the heuristic cost of the goal, target goal, is also calculated or also used for calculation. So this algorithm is more faster than registrar. So they use A star algorithm. Mostly you have seen in many of the cases you see the A star algorithm, because A star algorithm is more faster than registrar. Then comes to the method 4. These all algorithms which we are talking about they are just the traditional methods which are developed a little years ago. So the fourth one is the probabilistic roadmap. In this case, what they do is they randomly assign some points in the C space. They randomly assign some points in the C space, which evaluate from point to point from the obstacle distance, and then they make a roadmap by connecting all these points. And they use Dijkstra based algorithm for finding the start to goal position on these, joining by these points towards the goal. So this is a PRM method to find from start to goal position or trajectory planning. Then there is a method 5, you can that is RRT, Rapid Exploration Random Tree. In this case, they start like a tree. The branches of the tree is from the start position. They make whole space as a tree type, like they put some random points and they calculate it, start with the new points, and they goes on to hold the space till they reach the goal. So there will be a branches of trees which will be, and these branches will never collide with the obstacle. So whenever these branches which touch the obstacle, they stop it. So there will be a random tree formation throughout the C space, and all these connecting points will reach to the goal, and it will create a path to the goal, and it will be a planned trajectory towards from the start to the goal. So RRT is also a good method for trajectory planning. Then some more researchers have developed a new method where they make a start of the tree from both the sides, like from the goal and the start together. So this is a dual tree RRT, where they start it from the goal start point, the points from the start, simultaneously point from the goal. And the connecting between each this tree can save you a lot of the time for convergence. Then from the center point when it connects, it makes the path from goal to the start position, and it will generate your path from start to goal. So these are some methods where the trajectory planning through conventional methods are going on. But there are some different other evaluatory algorithms like ant colony, which are bio-inspired from the nature, like ant colony, firefly, honeybee. So these are the methods which are evolutionary in the case. They inspired from the nature, and they are the search-based methods. Like randomly they search the points by making the cost function and to reach the goal. So there are many methods upcoming day by day which use, but they all are the search-based methods. Means in the time, if you make it iteration by iteration, they give you a different path. It's not they fix you on the same path every time. Search-based methods can provide you n number of results by time, but they are the fast, and maybe they give you the shortest time frame and the shortest distance or shortest path length between the start and goal. But many of the times they are in some iteration they give you a different paths. So what is the method which gives you a shortest path, and every iteration you give the same path? So there will be a general. First we discuss general concept of obstacle avoidance, and the method which we have introduced is Newton's method with Lagrangian minimization. It gives you the same path at every time, and it gives you a very faster rate of convergence. So what first we'll discuss about actually the general concept of the obstacle avoidance. So these are the parameters, like the first A and B are the start and the end point, and this is a gear body or a robotic arm joints. We can say that this is the body of the robotic arm, and this is the point P where it touches on the trajectory. There will be an obstacle Q on the trajectory path. So this is denoted by Q, which is an obstacle coordinate. Then there will be the first point, first collision point, which is the point where initially collide with the obstacle, and it have a configuration of accept. This is the distance between the main body and the obstacle distance. PF is the main obstacle distance between the main body and the obstacle coordinate, or the center of the obstacle. This will be the last collision point. When it moves, after colliding, it moves to the last point. So it is the last collision point. And this is the distance between the centroid axis of the body of last collision point and the body of the arm. So this is our main consensus, that this is the robot collision region where the robot is colliding with the obstacle. So this is the important region of where this collision happens. Then what will consist is the heading point where this collision will start. So we make some point before the collision point, that they name it as a heading point, like obstacle avoidance head point, which starts the avoidance from there. So here is the obstacle avoidance head point, and there is a distance between the obstacle or head point and the obstacle. This is the obstacle avoidance tail point after completing the collision region. And this is the actual obstacle avoidance region where our main focus is on. Like whenever the robot arms have a trajectory from A to B, it has a head point where the obstacle avoidance region starts and a tail point where the obstacle avoidance region ends. And there is a major concern of the red obstacle collision region where actually the collision happens. So our main focus area is on obstacle avoidance region. So now this is the original trajectory. Actually, in case of obstacle avoidance, this point, head point, has to move to this point in order to avoid the obstacle. In order to avoid the obstacle. And this is the configuration, optimized configuration, which the effector has to obtain. So this D will be the main obstacle avoidance distance which has to be maintained to avoid the obstacle, with M as a optimized configuration. So the head point, whenever before the collision region, the trajectory has to be rearranged in order to avoid the obstacle in this way, and it has to retain this new trajectory. So this is the obstacle avoidance trajectory. So these are the points which are majorly in concern. Like initially, this is the head point configuration where this was the original point which was colliding with the obstacle, and this was the head point where we started the new trajectory planning before it's colliding, and we make 3 new points which avoids the colliding region and in sequence of the road configurations and to the tail point. So in this way we calculate the distance between the 2 points. Like this is the position and this is the new position. In this way we can calculate in between the 2 points of all the new points which are generated. So if we make a draw, we can see that the cylindrical space and this limit region where this a safe region is this point which is a safe distance from the obstacle, and all this inside this boundary, in this region will be your fail region where it will be colliding the obstacle, and the new region will be the limit state where the obstacle avoidance sequence of all the road configurations. So here we denote it by XM is the most probable failure center, and SC is a state escaping direction, which is a state we can use it for escaping, and the D is known as the danger factor. So we denote the distance from the obstacle to the robotic configuration through a danger factor, and we insist in our code that danger factor have certain values from 0 to 1, and which denotes the distance between the colliding point to the safe region. So what is actually the danger factor? This is the center axis of the body, and we have seen the distance between the obstacle configuration and the center axis. If this distance is on the center axis, the danger factor is denoted to be 1. If it's on the boundary or on the somewhat safe region, it is denoted by 5, just touching the border. And if it is far away, then the danger factor is 0 or is equal to 0. You can tell that. It's not always 0, it's equal to 0 when it is far away. So we make some calculations on all this and divided this problem into certain regions, where if in the red line we can see that the danger factor will be 1 when it is colliding with the center axis, and if there is a first region which is danger factor is of 0.5, here is we make a certain boundary and divided whole workspace into certain regions with calculated from a cylinder and a obstacle having a radius of R0, and the cylinder have Lj of length and Rj of its diameter. So, and the distance from the center is R. So in this way we have divided every space into certain space blocks, and some calculations have been done on all these separate spaces on the region, and observe that we have made a boundary of like danger factor is 0.5, which just colliding with the obstacle. If the body is just colliding with the obstacle, and all this region have certain develop certain equations using the model of a sphere as an obstacle and a joint as a cylinder. So now all these factors which we calculated as a region, Now we minimize with the allowable level of danger factor. Like we put the danger factor to allowable level, which should always, you can see that we should always be less than, like this is the allowable strength, but it should always be less than 0.5. 0.5 is your just a margin limit when it touches the obstacle. So after many calculations, we use minimization with allowable level of danger factor with xm and calculate like this objective function with take to that danger factor with xm and the obstacle coordinates. Then converting to the unconstrained optimization, we minimize the Lagrangian multipliers and slack variables. And finally iterate with the Newton's method, or solving all the Lagrangian minimization by the Newton's method, where we use the gradient vector as gradient matrix, and Taylor matrix is given by H. Now this is that was the optimization process of optimizing the multiple point on the new points, all the three new points which we have seen in here. Like these three new points, xm, xm minus 1 and xm plus 1, and this was our original point. From here we calculated three new points for obtaining a new trajectory. So in this method, we have a solution like from robot arm will move from A to B. It can generates all the end effector coordinates for Pi, get all the robotic arm configuration as Xi. Now it will check whether these Xi will collide obstacle Qk. If it is not colliding, it is directly execute from A to B. And if it collides, then it first determine the XF and XL, like tail point and the first point, heading point. Then determine the head point and the tail point. Then it solves for xm for each xm origin. Like for each xm origin on the trajectory in the obstacle avoidance region, it will calculate three new points. For like xm minus 1, xm plus 1, three new points on the new trajectory with allowable danger factor less than 0.5. And the curve will be fit for obstacle avoidance trajectory. And update the robot configuration for avoidance region and execute the movement from A to B. So this is actually the procedure of trajectory planning using Newton's method. So this was a procedure which is iterated in the previous optimization problem. Like initial guess of xm to xm origin, iteration begins with t to 0. Then it evaluates the gradient and Hazel matrix. Then it generates an objective function and using Newton's method, it calculates it. Then have a conversion check. If it is not converged, then it again iterate, and this iteration goes on till it converges, and return to the optimal designs by having xm t plus 1. So it will give you a three new different points on the new trajectory by avoiding the obstacle. So this is a demonstration for the Newton's method. Like there was a heading point here. P1 is a point on the collision region. P2 is the next point on the collision region. P3 is the third point on the collision region. In this way, P1 to P3 it is colliding with the obstacle, and there is a tail point. So in this way, we can see that it is colliding with from PH, P1, P2, P3, and P So this was the robot collision region. So now it was the P1 original. Then there was the first iteration, second iteration, and P1 optimal. This will be the new P1 point. Then P2 original, then iteration, then P2 second iteration, third iteration, and then P2 optimal. So in this way, it will iterate and find the optimal point. And this optimal point will be depend on the allowable danger factor, which is always less than 0.5. So we iterate it for more danger factor and find out that 0.4 is the allowable danger factor. This way you can get the third optimal point. So this was the initial robot collision region, and this was the new trajectory plan on that region. Now you can see this demonstration on the actual video. Here you can see that these are the obstacles here, and it generates a new trajectory. And why this method is good than other algorithms, because it's not a random search based method. It doesn't search in a random way. It only justifies on the obstacles and the danger factor which we allow them. This was with other robot brand. That was about the obstacle avoidance, which we are talking about. So it was for the generation of the trajectory replanning when the certain obstacle comes in between the robot path. But what about the second part, like human motion recognition? So for human motion, first was the part was already we tell about the first part. It was for predictive planning when it comes about human robot collaboration. The second part was motion detection, human motion detection, because when the robot knows that your screwing action is over, to do the second option. So that the second part of human robot collaboration is human motion detection. So for this work, we use STGSN. STGCN is a deep learning network model for human action recognition, which was published by Anadol in 2018. It performs human action recognition independently without the interface of shooting scenes, and only needs to consider a human joins in each image with good computational performance. The spatial relationship between the individual joints and the temporal relationship between the same joint in each frame are automatically learned, which makes to perform well in large data sets. The model collects coordinates from original image to media pipes and converts them into graph structure. What is actually the STGCN do? They use a media pipe. Media pipe means you make a human body, a skeleton. We see that the human body is a skeleton, and we named every joint with some numbers. So every joint you can see they have like fingers. You can take a head or the body, the legs. So everyone has the numbers, and we make that the human body is the skeleton. So now from the camera, each joint has been trained and each can look like a skeleton of a body. So SPGCN model also considers spatial information, like same joints of the human body in each frame. You can see that the joints in each frame will be the same. Like whenever the camera will detect the input video, the post estimation of the joints will be same in each frame, and it is always connected to the neighboring joints in the same frame. So figure 2 it shows the action recognition results of the red joints are affected by all the neighboring joints, including the connected joints in the preceding frames, which are marked as red lines. We can see that if there is a hand or action in the red frame, here these points will be like coordinate with the same frame if we are having some different action. So there will be a classification of this into one action and this into one action, and all these joint points are classified according to the action, and this red line which shows that the right hand is in up position. So it will make a score, and all the points on the frame will be trained, and it will show you that which gives you a highest side score of that particular points. So the final trained SPGCN model is used to identify the human joints in each frame, and the model will return a most likely action recognition by using softmax classifier. So here you can see that there is an assembly task of an acrylic sheet placing a screw, and you can see that how each joint is being looked to the camera. So here we have seen that it is of the assembly task, which was of acrylic sheet. The screw we have placed the screw and lock the acrylic sheet, and so it goes under the human motion, and whenever it's completed its task, the robot will do its action. So it is about the human motion action detection. Initially we calculated the trajectory planning, and here we are doing the action recognition. Now it's both if we can combine trajectory planning with human motion recognition together. Now you can see that using media pipe SPGCN, the body looks like a skeleton. If there is a hand in between the trajectory, you can see that the new trajectory has been formed. So that was the model for human-robot collaboration with trajectory planning and human motion detection. So both of them we have seen in one single experiment. But you can see that where how we can find. So what we have done in our work is we have made like had a number of some points as a sphere, because we have used a sphere demonstration in our trajectory planning. So we have used like certain points to be incorporated as a sphere, and that sphere, the trajectory planning works on using the sphere, not individual joints. Like 2 or 3 joints can be plugged to make a one sphere. So I can explain you whole how the man-machine collaboration collision avoidance system can work. Like there will be like a scenario where the robot and a human has to work together. So there will be a camera installed, and all the robot arm is controlled through a robot controller, which will go to an application server, and the camera will detect the image processing and robot human distance and get the 2D and 3D points. This will be your camera module, and there will be a decision making module of the system which optimizes all the points. And this decision making module, where there will be 2 types of system which is demonstrated here. Like initially when we started this work in 2019, we just tried it if some humans are coming towards close to the robotic arm which is already doing some specific task. So if it comes very near, it slows down. Like when there will be a speed of 50%, there will be a speed of 25% or stop. So there will be a module called, like whenever is on autonomous system, where there is no human working together with the robot, but that should be in a safety mode. So whenever if you come very near to the robot arm, it will reduce its speed of working, and if you are very near, then it will be reduced to stop. So this was our first model of human collaboration system. Then we integrate more by avoiding module. Like the obstacle data is coming, then detecting the danger factor, redefining the trajectory. So it is an add-on to this system for avoiding the trajectory module or avoiding the obstacle module. Then it will all go to the application server and it controls the robotic arm. So this was the complete man-machine collaboration avoidance system which we have developed in the past years. Then our next phase is what already I talked in the last class also. Like what we are going to do with the generative AI. So it's like the same. Right now we have seen that the humans is there. We are getting a human motion recognition. We are getting a laser guidance system for the particular which part of you want to work or how it is done. Having a robot obstacle avoidance. Now everything is there, but it is have a lot of complication algorithms which are already predefined. But what happens when there is a certain something or certain change of work space or change of your target work. If you are doing something on a specific task which is already assigned by the robotic arm, it's okay, it's working fine. But if something you want to change, like if you want robot to stop the work and do some other task, like hand over the tool A to me. If there is a tool set which is predefined, okay, he has handed already a plate to you, but you want a different screwdriver to screw it. So you can ask the robotic arm to do that, but how it will work. So we use a large language model and generative AI to get a new specific set of rules for doing that work using generative AI. So this will be the next generation target area of doing the same thing with generative AI. Also there was with human request recognition using GAI. I am not more familiar about this, which is Professor Ling's work. Yeah, it is also similar to the generative AI which we are seeing here, but it used some documentation. Like they extract the text from some documents and search on the documents and regenerate a new set of plan. It's related from the documents. Like we already assigned some documents which have some plans, and if we want to implement that plans, we just send it to the OpenAI and it will remake it and make a request and regenerate the new plans. So this was the demonstration of that one with human robot collaboration with generative AI. Like in this case, we are seeing that whenever the robot is in like obstacle is in the first position, and if it suddenly changes its place, the robot arm is always taking its again new avoidance region. So this is also like a dynamic obstacle avoidance. You can see the laser guided system, which is guiding where to put the screw. We have seen that they have made some audio segment to the robot to change its orientation. They are speaking something to change its orientation. Here we have introduced three different research areas, where the first was the trajectory planning, the second was the human motion recognition, the third is the laser detection or the laser pointing, the autonomous laser pointing where the job has to be done. us see the GAI and all the which we have discussed in the earlier slides. Let's have a 10 minutes break and we'll join for the next meeting. And what are the key factors which we discuss is the trajectory planning, human motion recognition using SGCN and the laser detection for perfectly where the work has to be done. There are also some other extended research works which we want to discuss with you. After that, after this discussion, Professor told that you can discuss or about your project work, because this is the last class of the robotics. So maybe you can discuss about your project work, and if you have some doubts also you can discuss with me. So there was a motivation for high payload picking and placing robots with a minimal requirement. So here we can see that we have seen one video where we can see there is a certain doing different job works. There is a certain robotic space with the rails doing various types of works together in one environment, like taking a job work piece from the rack, taking the tool, taking the tool, getting the work piece which has to be dropped. So in this scenario, what we have seen, the advantage is modularity, high payload, flexible layout. Like payload can be high, which can have a flexible layout. But what is the scenario? It is in a closed environment. The robot cannot do other works. It cannot have the factory space is very high. Or distance between the two, like from the tool room to the object or to the CNC machine is a large gap. But it cannot do the same thing. It have a lot of cost in maintaining all the equipments. So to improve the higher flexibility, smaller space, more applications, it was our motivation to develop a mobile manipulating robot. Mobile manipulating robot means a robotic arm which can be mobile, which can be travel in different parts with high payload capacity. So our research direction goes to an automatic guided vehicle which should have a high payload capacity, which should also incorporate a high payload robotic arm in this, which can freely work. So in all, there will be a 9 degrees of freedom. 3 for the mobile robot platform and the 6 for the parallel robotic arm. So here the first developed in 2019 or 20, we developed a mobile AGV, which automatically guided with the heavy payload capabilities. So it have 3 degrees of freedom, it can roll, it can rotate and guide, and it was almost 600 to 700 kg, the total load of this. It have 4 maximum wheels with 4 motor, which powered each wheel in a separate way with battery. So this was the starting of the high payload ground vehicle, which was the motivation for the started that we want to develop a mobile manipulation robot. Then we go for structural design. It has a 3700 watt brushless motor, which have a maximum torque of 120 Newton, have a Magnum wheels. Then we integrate loading capacity of 70 kg with a KUKA robotic arm, which have a maximum speed of 2.5 meter per second and a power consumption of 70,000 watts. Also we integrated IMU, LiDAR and IPC so that it can be an autonomous vehicle, no other, which can be powered from the battery. And this was a circuit diagram of autonomous mobile robot, which we want to develop. And right now it is already being integrated. From past 6 years we are working on that. So this is the current version of a high payload autonomous mobile manipulating robot, and it's almost more than 1000 kgs in weight, the total robotic arm, having a 70 kg payload capacity and work for 9 degrees of freedom. If you want to see this one, is in Industry 4.0. Whole chassis is supported by a small 4 wheels, multi-directional wheels in the center of this part. So have you seen that due to the weight, it is seen that the floor is damaged. So right now we are working on how these wheels can be changed in order to make it freely movable in any type of floor. Then that was one of the projects for that. Then we have another AMR design. We have seen that the flexible circuits, they are come into the roles. For the inspection of flexible circuits in the industry, they want these circuits. Actually, there are female workers which see the inspection of these circuits. So these circuit boards are heavy, like from 15 kg to 40 kg. So they need some autonomous robot which plays this circuit to the machine, which rolls, like it's a rolling machine from one roll to another roll, and it's a physical inspection, inspected by the machine and the co-workers together, and then this roll has to be placed to the place, storage, and another roll has to be bring to that position. So they want us to develop a mobile robot which takes this roll, flexible circuit rolls, and place to the storage area, and again take the new roll and so the machine. So we develop a different machine where there has a 2-layer. This is called a chassis layer and this is called the application layer. For loading and unloading, you can see the video of the live demonstration of the mobile robot. We have placed a gripper here because the rolls, we cannot pick it from outside. These are very sensitive fiber circuit board layer. It is a hollow from inside, so everything has to be picked from inside. So we make a gripper which can be gripped in the outward direction to hold it. And it has to be, you have seen that the action recognition can move this robotic arm because there are spaces limited. So with the hand actions, it's smooth. So these are the PCB rolls. grips from inside. So this mobile robot which developed and which have a factor of safety of 28, so it is highly safe and it has a payload capacity of 15 kgs right now. But they are asking us to, it has to be upgraded to 40 kgs because the biggest rolls are of 40 kgs. So it is jointly developed with ITRI and Taiwan. So it was the last slide. I think Professor was likely to have some robots which can play the basketball. So it was slides from Professor Lim. Okay. Thank you very much for today's. If you want to see this, both of the robots, you can just join to Industry 4.0. The both of this one and this both are placed there right now. Now it's a discussion time on your projects. If you want to discuss with teammates, you can discuss with each other. If you have any doubts, you can discuss